This code imports necessary libraries and modules for building a convolutional neural network. It also sets up the environment for using Plotly for visualization and initializes seeds for reproducibility. This code reads two CSV files, one called train.csv and one called test.csv, and converts the date column in each file into a date object. It then stores the contents of the files in the variables train and test. This code calls the describe function on the train object and outputs a statistical summary of the data contained within the object. This code prints the first 5 rows of the trained dataset. This code prints the minimum and maximum date from the date column of the trained dataset. It uses the .min and .max functions to find the earliest and latest date, and then converts them to a date format before printing. This code calculates the difference in days between the maximum date in the test and train datasets and prints out the maximum dates from each dataset and the resulting forecast lag size. This code takes a dataset called train and groups it by date, store, and item, and then calculates the sum of sales for each date. It then returns the total daily sales, store-specific daily sales, and item-specific daily sales. This code creates a scatter plot of daily sales data, with the date on the x-axis and sales on the y-axis. It also adds a title and labels for the axes. The final step is to display the plot using the applet function. This code stores the daily sales data for different stores in a list and creates a scatter plot showing the sales over time for each store. It also adds a title and axis labels to the plot. This code takes in a data set of daily sales for different items, then creates a scatter plot for each item, using the date as the x-axis and sales as the y-axis. It then adds these scatter plots to a larger overall plot, and displays it using the applet function. This code creates a new variable called train and assigns it a subset of the original train data that contains only the rows where the date column is on or after January 1, 2017. This code first sorts the train dataset by the date column, then groups the data by the item, store, and date columns. It then calculates the mean of the sales column for each group and assigns the result to a new data frame called train_GP. Finally, it renames the column in train_GP to sales and shows the first few rows of the data frame. This code takes in a dataset, a window size, and a lag value. It then creates a supervised learning dataset from the input data by shifting the data to create a sequence of past and current time steps, as well as a target time step for prediction. It then combines all the columns and drops any rows with missing values before returning the new dataset. This code defines 3 variables, window with a value of 29, lag with a value of lag_size, and series, which is equal to the result of a function call to series_to_supervised with parameters train_gp.drop, date, axis equals 1, window, and lag. It then displays the first few rows of series using the .head function. This code first creates a variable called last_item and sets its value to a string formatted with the variable window. It then creates another variable called last_store and sets its value to a string formatted with the variable window. The code then uses these variables to filter a series and reassigns the series variable. This code drops specific columns from a series of data based on a window and lag. It also drops additional columns related to the item and store being analyzed. This code creates a label for a given column by adding a lag size, and then creates and drops a series for that label. It then splits the series into train and validation sets, with the train set being 60% of the original series. Finally, it prints the shapes of the train and validation sets and displays the first few rows of the train set. This code sets the number of epochs to 40, the batch size to 256, the learning rate to 0.0003, and the type of optimizer to atom with a learning rate of 0.0003. This code creates a neural network model using the sequential function. It adds a layer with 100 neurons and a rectified linear unit, ReLU, activation function, with an input dimension based on the shape of the training data. It then adds another layer with 1 neuron and no specified activation function. The model is compiled using a mean squared error, MSE, loss function and an atom optimizer. Finally, a summary of the model is printed. This code trains a multi-layer perceptron neural network model, defined as model_MLP, using the training data, x_train and y_train, and evaluates its performance using the validation data, x_valid and y_valid, for a specified number of epochs, with a verbosity level of 2. The training history, loss and accuracy during each epoch, is then stored in the variable MLP_history. This code reshapes the values of the x_train and x_valid datasets into a three-dimensional array with a shape that matches the original datasets. It then prints the shapes of the newly created arrays. This code creates a sequential model for a convolutional neural network, CNN, for predicting data. It adds layers to the model, including a convolutional layer, a max pooling layer, and 2 dense layers. It then compiles the model and prints a summary of its structure. This code trains a convolutional neural network, CNN, using the given training data and labels, validates the model using the given validation data, and then records the training history for the specified number of epochs. The verbose equals 2 parameter prints the training progress during each epoch. This code creates a sequential model using LSTM layers with 50 units, a ReLU activation function, and an input shape based on the number of features in the training data. It adds a dense layer with 1 unit and compiles the model using the mean squared error loss function and the atom optimizer. It also outputs a summary of the model. This code trains a LSTM model using the provided training data, validation data, and number of epochs. The fit method returns a history object which contains information about the training process. This code creates two subsequences for each time step in the input data, then reshapes the input data into 4 dimensions: samples, sequences, time steps, 1. Finally, it prints the shape of the newly created training and validation data sets. This code creates a sequential model and adds layers to it. The layers consist of a 1D convolutional layer, a max pooling layer, a flattening layer, an LSTM layer, and a dense layer. These layers are configured with specific parameters such as the number of filters and kernel size for the convolutional layer, the size of the pooling layer, the activation function for the LSTM layer, and the loss function and optimizer for the model. This code prepares the model for training and can be used for predictive modeling. The code trains a convolutional neural network (CNN) model with long short-term memory (LSTM) using training and validation data sets. The number of epochs and verbosity of the training process are specified. The results of the training process are stored in the variable CNN_LSTM_history. This code creates a figure with 2 by 2 subplots that share the same x and y axis and has a size of 22 by 12 inches. It then plots the training and validation losses for 4 different models, MLP, CNN, LSTM, CNN-LSTM, on separate subplots, with each subplot having its own labels, title, and axis labels. Finally, it displays the figure. This code trains a multi-layer perceptron, MLP, model using the input training data, x_train, and corresponding target values, y_train, and then predicts the target values for both the training and validation data. The root mean squared error, RMSE, is then calculated and printed for both the training and validation sets to evaluate the accuracy of the predicted values. This code uses the trained convolutional neural network (CNN) model to make predictions on the training and validation data sets. The root mean square error is then calculated for both sets and printed. This code uses a long short-term memory (LSTM) model and a convolutional neural network (CNN) model to make predictions on a training dataset x_train_series and a validation dataset x_valid_series. It then calculates the root mean squared error (RMSE) between the actual values y_train and y_valid and the predicted values LSTM_train_pred and LSTM_valid_pred and prints them. This code uses a trained model, model_CNN_LSTM, to predict values for a given dataset, x_train_series_sub. The predicted values are then compared to the actual values in the dataset, y_train, using the root mean squared error, RMSE, as a measure of accuracy. The same process is repeated for a separate dataset, x_valid_series_sub, with the resulting RMSE values being printed for both the training and validation datasets.